If we let x sub 1 all the way to x sub n be a realization of a random sample from a Pareto distribution with parameters a and 1, what is the maximum likelihood estimate for a? Your first instinct here might just be to write out the Pareto distribution PDF if you have forgotten that. That's this guy here, where f of x equals a x sub m to the power of a over x to the power of a plus 1 if x sub m is less than or equal to x and 0 everywhere else, right? Where in this case, our x sub m is really 1, right? So that simplifies our PDF a bit. And then you might wonder, okay, what's our likelihood function going to be? So we have big L of a, right? That's just going to be the product over all of our xi's. But since we don't have an x sub m, we have this guy here, right? Where we have a large L, L of a equals our product of a over x sub I to the power of a plus 1 for all our i's. And then if we take the ln of that, right, the natural logarithm of that, you're going to see that that becomes a sum due to the properties of logarithms. And then again, right, once I move my logarithm within my sum, I can use the same property, and now since I have a fraction, it will become ln of a minus ln of x sub I to the power of a plus 1. And now you'll see already there's further opportunity to simplify our maximum likelihood function here, right? Since ln of a doesn't depend on I, we can just move it out of our sum. And also, using that same property, right, we can just move a plus 1 to the front of our sum, since it was the exponent of x sub I. And then when we take the derivative of our log likelihood function, and we set that equal to 0 to find the maximum, you'll see that it's n over a minus our sum from I equals 1 to n of ln x sub I, where we drop the a plus 1, right, because plus 1 of the sum is constant, or like constant when we look at a, right? So we just ignore it, we get rid of it. And then on the most right-hand side, right, that's just a bit of algebraic manipulation, and then we get a equals n divided by our sum. And then we're done.